So I'll just recap the theory that we learned because that's going to inform the lab that we are going to do today. So what we learned was the topic of explainable AI. Now, this is gaining a lot of importance these days because we have realized, if anything has shown us in the last 2-3 years, it is that black box AI can do a tremendous amount of damage. In fact, the scenes that we are seeing in the Capitol Hill today, this mob, it has been indoctrinated through the recommender systems of this giant, uh, you know, web things like Facebook and Twitter and Google and so forth. At the end of it, our technology world has to pick some of the blame for what's happening today. So, and that has raised this question that, see, we don't even understand what we have built and how it is working. And that is not okay. It will tear apart a country. It will tear apart the fabric of civilization. We need to, there are very dire consequences and practical things. If from a medical perspective, you would want to know why the model, why the machine is saying that you are less likely to get diabetes than the next person. Right? So that that has caused a lot of research in the recent years. This research has also been fueled by some high-profile failures, like the facial recognition failure, in which senators were identified as essentially serial killers and rapists, the Black Caucus, and other problems, like, for example, Amazon's the hiring system, which without explanation would recommend who to hire. And it turned out on investigation that it had severe bias against the protected classes. Now, obviously, if they could see that it is doing that, they would probably, let us hope, that they would not have implemented it. But they couldn't see it. They couldn't see the bias in the data and the bias in the machine. Many years ago, there was a similar case, I believe, against Kronos, which also tried to do algorithmic hiring. And from what I remember, they lost the case. They had to pay a tremendous amount of money in damages. So, so that has been there. So that brings us to the whole emerging and hot topic of explainable AI or explainable machine learning. It has even developed its own acronym, XAI, people use. So traditionally, they believe that there is this graph that you see with red color. This graph shows, maybe I can zoom into this a little bit more. This graph, it shows people used to believe that models that are highly interpretable, they don't perform as well on complicated situations. And models that are high performing are essentially black box, opaque models or low interpretability models. And people were getting comfortable with that for many years, for almost 20 years. I remember at the turn of the century, the debate amongst researchers was that, is it like, till then it was a given that you would have a proper theories explaining what the model is doing. Then came the ensemble methods and the kernel methods. And in both of them, it was very hard to put a concrete, simple interpretation about what the model is doing actually in making those accurate predictions. And there has been a debate for 20 years about, is it okay to just have a machine that has high performance, high accuracy, but is a black box? Well, so people often believe that you can't have it both ways. You can't have the cake and eat it too. So now that brings us 20 years forward, and we realize that now we cannot have black boxes. We need to impose explainability onto the model. So now what people are trying to do is they are saying that, in a sense, this thing needs to go up here. It needs to be high performance and high human interpretability. it is not acceptable for it to have low interpretability. So that brings us to this whole topic of how do you do that? When you think, especially in the context of a deep neural network, you realize that we deliberately bring about an activation function that does a nonlinear transformation. Without a nonlinear transformation, you would not be able to achieve the universal approximator theorem. Right? You can't make a neural network a universal approximator. So once you bring in at each of the nodes a nonlinear transform, output of that goes to the next node, which also does nonlinear transform. Pretty soon, it becomes almost impossible to interpret what the overall function f is that it is using. You know it exists, but you don't know what it is. And so that becomes the problem. So now, to explain this, I talked about a geometric perspective. I said, let's see, how would you achieve interpretability? When you have a function which globally is very complex and captures a complex reality, at the end of the day, if you make a hypothesis that the function is some manifold, embedded manifold in a feature space, then a manifold, and I gave you an example, is sort of like a bed sheet without tears or creases, a smooth sheet, but it can be turned whichever way. That's the intuition behind manifold. And now locally as in the eyes of an ant or a bedbug crawler, the world looks flat, just as to humans who are very small compared to the size of the earth. The surface of the earth doesn't look spherical or ellipsoidal. Instead, for the longest time, to us it looks flat, and for centuries, mankind believed that the earth is flat. Okay? Because that is the evidence our eyes are bringing to us. And it goes to show that in the very small, these manifolds, they look flat or they look Euclidean. So they look like a flat map. You can draw a Euclidean thing around it. And as an example, I just said that, say, suppose you take a curve like this, then if you look at this point, you can make a little yellow neighborhood. And in the neighborhood, it is essentially flat, right? And then I brought in this little bit of Taylor expansion saying that the value in the neighborhood is the value at the center plus the slope times the displacement, the gap between x and x naught, and along with high order terms. And the point is that if delta x is very small, you can sort of ignore the high order terms, and you can assume that there is no curvature, etc., because locally it will be flat. So based on that hypothesis, when you generalize it to higher dimension, one of the things that we realize is that in the very local perspective, anything, no matter what it is, you generally end up with a approximation, which is an additive model. That in the very neighborhood of this, you can build a small additive model. Now, remember the word is local, very locally. So the people have been asking, let's say, suppose you have a function which is unknown. You can always try to approximate it with a less complex surface, a less complex curve. Let's say look at this white curve here, which is complicated. You can try to approximate it with the yellow line. So you make a surrogate model which approximates the original model. Now the question is, what is the fidelity of the surrogate model to the actual F, which is analytically intractable? So, well, globally, it's a bit hard. Like you see that the yellow line and the white line are not exactly the same. But obviously for the math that we talked, locally, we can rest assured that we can build models high fidelity. So anyway, so the thing is, we agree that locally a surrogate model can approximate the unknown, the rather intractable function with a fairly high fidelity. So that brings us to the concept of line, which is that let's build a local interpretable explanation. And it doesn't matter what the model is, that F may come from a neural network, decision tree, random forest, you name it, because it doesn't matter. At the end of the day, mathematically, it is some manifold, right? To the extent that it is some manifold, therefore, Locally, of course, it will be flat, right? And so one of the simplest explanations that you can do is you can essentially do linear regression with some, additions. You do a kernelized linear regression means you're more sensitive to points closer to the point that you're trying to explain and less sensitive. You do that and you regularize and all that. Everything that we learned in linear regression theory, the adaptations of linear regression, you do that, you can get away with it. Or you could do a decision tree, but decision tree, keep it very, very simple so that people can understand it locally. And so what you do is you create a loss function which has two terms. You say, give me G is the explanation, the surrogate model. You say, give me the simplest explanation, that explanation which has which maximizes the fidelity of G to F in the neighborhood of X, the point that you're trying to explain, point in the feature space that you're trying to explain. In the neighborhood of that, G should have a very high fidelity to F. Otherwise, you will have a loss. L stands for the gap between the two in some form. Right? Now, this term, the second term is the complexity term. It just guarantees that G cannot get too complicated. So in the case of a linear model, it's reasonable, but in the case of a decision tree, for example, a decision tree can become arbitrarily complex. So you need to guard against it by essentially regularizing it with a complexity penalty term. And so that's how line works. Now, there's a bit of technical details of how it picks points. What it does is in the neighborhood of the points, it will do a Gaussian sampling. And after that, it will apply a weighted distance kernel, means give more emphasis to points which are very close, and then use that to build a local model, right? And it generates synthetic data by perturbations of the real data. Once you have the model, once you have this black box model F, I can take a point and I can generate a lot of points in the neighborhood of that point. Right? These are the perturbations of that data point. And so feed it into the function. Once I feed it into the function, I'll get some output. And now I have new synthetic data, which I can now build a simpler model to explain in the local context. So that is line. So we'll do a couple of labs with line. Then there is Shapely. Shapely answers the question, well, in a sort of a, without,
Asif,
yes.
so what does fidelity means,
Oh,
like in this context?
oh, fidelity. Fidelity is how close one thing is to another. So suppose I say, let's take an example. Suppose you make a curve like this, and you have a, sorry, you make a line like this. This is A. Right? You make another line which goes like this, B, and then you make a third one which goes like, of these, which one would you consider closest to white or the closest imitation of white?
The yellow.
Yellow one. So you would say that the yellow has the highest fidelity of the three.
Okay.
So fidelity is how closely it mimics the other, so that if you could replace one with the other, nobody would notice. Right?
Okay.
So that's the point. So that's fidelity. So now Shapley takes a slightly different approach. It doesn't take a geometric argument. It takes a game theoretic argument, and it does an interesting thing. It says that, see, if you want to find out how important a player is, in this case, a feature is, create every single model that doesn't have the feature. So that is obviously it's a NP hard problem, because an NP problem, not NP, NP problem, because it will be exponentially large number of combinations you can do or coalitions you can form without this player. And then each coalition, you see the performance of the model with the player and without it, right? And then at the end of the day, you go and take some form of average of the difference between them. You'll know how much this player has contributed. Then you do it for the other. Now, this has one advantage. It can be both local and global. Why? You can do it across the board and you will get a rough and ready a global sense of feature importance. Right? But more importantly, we know by now that see global feature importance is really not meaningful. To me, it's just a rough and ready measure. What really matters is in regions of the feature space, locally, how do the features matter? So you can play this game locally also. You can find out how the model performs with and without a particular feature, right? And see. So you can come up with local values. And so therefore it begins to look like line locally, but it takes a more game theoretic argument. Excuse me. So that is Shapley. Shapley again is a, when you think through the implications of this, you realize it's a lovely, simple idea, but extremely powerful. Right?
So, Asif, I have a quick question. So when you say that you're removing one feature and then, I mean, you're freezing the model in the first place, and then you're removing one feature, and then seeing what would be the output with the rest of the features going through the network?
No, it's not like that. Okay, let me re-explain it. Suppose, let's take a game in which you have 4 features, just to keep it simple. You have features x1, x2, x3, x4. So what you do, suppose you want to know for x1, right? For x1, do one thing. What are the combinations you can do? You can do, so here, this is called the power set in set theory, power set. You create the power set. Your power set will contain 0. It will contain x2, sorry, a set of x2, right? A set of just x3, a set of x4, right? And then it will contain another set of maybe x2, x3. It will contain another set of x3, x4, and then another set of x2, x4, right? And then it will contain a third set of x2, x3, x4. Maybe I'm just writing it over, x3, x4. Do you agree with that? This is the so-called power set. These are called coalitions. In the world of game theory, this power set is essentially the coalition.
I see. So these coalitions are between the features, right? 4 features.
The 4 features, yeah. So what you would do is you have some target variable y. You would take the same model, but you would train it differentially. You will build a lot of models. So take an example. Suppose you want to take this. So you will build model A and model B. Model A will be built with x1, x2, x4. Model B will be built with just x2, x4. Are we together? And so you would see the loss here, loss A and loss B. And what you're looking for is the difference between loss AB for feature 1, right? And you do this game, AB game, with every element of this power set or of this coalition, right? And
so
when
I
you
thought
average it,
doing things locally, but looks like we are building a model from ground up.
Yes,
So,
yes. The original Shapley says that you just build a model. So what people do is that they then sort of do performance optimizations. They'll bring in kernel methods or something to make it not so brutal, right? But if you really think about it, even with 4 variables, you see that the number of models you'll be building is huge. That is why Shapley runs very fast. And you are only done with x1. Then you'll repeat the same thing for x2, repeat the same thing for x3, repeat the same things for x4. And once you have found the average losses, the average differences that x1 makes, x2 makes, x3 makes, x4 makes, now you get a sense of their contributions. That's the point of Shapley. Now, when you think about it, it has a lot of nice mathematical properties, which I won't go into. It's a little bit gets technical, but just assume that it has nice and robust mathematical properties. And it is robust against, one second, it is robust against things like a lot of correlation between variables, which you remember completely screws up linear models. So it is pretty robust against all that. Go
Yeah.
ahead.
Asif, I got the intuition here of the global. Could you just pinpoint how
Same thing.
local?
If you want to do locally, what you would do is, suppose you want to explain this result. Let me call it x naught, which is made up of some value, right? X1, x2.
Specifically in case of Shapley, I got the global.
I'm explaining that. Just be patient. So of this particular point, right? And you have the y, right? And you have a model n, right? So now think about it. In your complex manifold, right, that explains, it is this point. This is your x naught. All right. Now, what you do is you take a neighborhood of this. Again, I can take a neighborhood of this point and generate a lot of synthetic data, isn't it? I can take this data, input data, first do the same thing. First generate synthetic data through perturbation. Perturbations are small deviations from this x0. And next, feed it into that data, feed it into the model, M, whatever model has been built that you're trying to explain. And you will get therefore the y of those values, right? Isn't it? You'll get the y hats.
Yeah.
Right? You give this x in the neighborhood and you'll get y hats. Now you have a data, you have a model, but now you start playing the game. You build locally, very locally, you do the same thing that we did. You figure out in this region, whatever this thing is doing, which features matter more. Are you getting it?
Yeah.
That's it. What you play globally, you can do it locally. And in fact, the power of Shapley, and when we do the lab with the shape package, the power of the shape package is that, so the shape pack, the library of in Python, and it has been ported and all that. It is actually one of the libraries I like very much. It's very well implemented. I say that as a person who has implemented it from scratch. Yeah. So, because it pretty much covers just about all the major things you can do with Shapley. More importantly, you see using that the factors that influence in one region of the feature space are very different from factors that matter in another region of the feature space. Okay? So I took an example, right? So if you live in a middle-class commuter town where everybody wakes up, gets into their car or public transit, and then they all show up to work in San Francisco. Right? That is one community. The house prices will have middle class values, right? Well, Bay Area middle class values are, I guess, 1 million, but let's take a normal US middle class values, maybe 200,000-300,000. Then you go to Mac mansions, people who, another neighborhood where the house prices start at 5 million, right? So what is it, 17-mile drive? Is that right?
One of them.
Yeah. So, and you come across all these big Mac mansions there. So I'm guessing that those houses are all in high millions. Okay. So now look at the one factor, proximity to highway. In the middle class neighborhood, proximity to highway will probably, I'm guessing, be a positive factor for house value. Nobody wants to live in an interior where just getting onto the highway will take 20 minutes, isn't it? Whereas in this place, in a Mac mansion area, they deliberately stay away from the beaten track, right? They'll be on the beach or wherever, and they would rather no highway when near them. Right? So there, the proximity to a highway will have almost an inverse relationship, isn't it? You probably know, right? For example, in California, one of the biggest reasons we are not able to have high-speed trains is because all the wealthy neighborhoods have protested. They don't want the California high-speed rail to go anywhere near their towns, and which creates a huge problem. So, so you see, right, at different places, different regions of the feature space, the factors that matter are different. And the same factor matters in different ways. Here it could be a positive factor, there it can become a negative factor. Are we making sense, guys? Is the intuition coming across from what I'm saying?
Yes.
Yes.
That's that. Yeah. Another example is diabetes. In a 5-year-old, you don't want to ask the child to lose weight. Most likely 5-year-olds are 3 years old, not obese. Well, I don't know, modern world is different, but normally, 5, 6 years old are skinny, highly active kids. If they have diabetes, you don't suspect it is because of bad lifestyles or something. You suspect more fundamental causes. In a 40-year-old, you suspect that if it is adult onset diabetes, that there's some lifestyle component has something to do with it. Okay? So what factors matter depends upon the region of the feature space. Right? And that is what we are talking about. And that Shapley and Line, both of them, local interpretations, they give a very good job of it. Yeah? And in terms of visualization, Shapley produces, the Shape package produces beautiful visualizations that really helps you understand what is going on. I like those. And so I'll start the lab now by doing that. But before I do that, let me just finish the review quickly. So that was that. Line, Shapley, we did that. The last we talk about is when it comes to images, we talk about the saliency maps. And the saliency is what matters. What in a picture, if you have a cat, why did you call it a cat? Right? Where were you paying attention to most? Right? So as you probably know, human beings, when it comes to animals, it's an easy answer. Human beings, at least, are extraordinarily biased towards facial, to bias towards the face, towards the eyes of any animal. Right? Eyes and mouth and so forth, the claws, I don't know. So the face of an animal. All animals are keyed like that. They look for each other's facial expressions, mammals at least, right? But it raises the question that if we recognize animals by looking at their faces, what does a neural network do? It turns out, interestingly, as we'll learn in this lab, that neural networks actually, surprisingly, they come to pretty much a similar method. They learn to pay attention to, or they create a saliency map in which they're paying more attention to, or they're much more sensitive to changes in facial regions. Right? And how do we do that? The theory is very, very simple. We realize that if the derivative, another way to interpret the derivative is the sensitivity of the response to input. So if you look at the derivative of the response with respect to each of the input features, you will get which feature is proving much more sensitive. In an image, because each feature is a pixel, which pixels are important, and therefore you'll realize that the pixels around the face have an extraordinary influence in the decision that the neural network is making, in the prediction that the response from the neural network. Right? And that is a sort of a just elegant and simple argument. Of course, you have to cultivate that argument into more and more and more things. So it uses the gradients. Now, when you do this, the only difference between back propagation when you're training a neural network and when you're trying to explain a model is in training, the weights are adjusted. The weights and biases are parameters of the model, and they are learning. They are fluid, they're changing, they're getting better. Once a model has learned, you freeze it. No more back propagation of the parameters and updates of the parameters. Right? So remember the step was you go the forward pass, compute the output, compute the loss. From the loss, so here's the thing. You go the forward journey, you compute the loss, you take the gradient of the loss, number one, you take the back propagation, back propagate the gradients all the way to the first layer, the weights everywhere. So all the weights know the gradients. And then the next, they all take one step forward, right? The gradient descent step. And that's how they progress. But in this, the model has already learned. So you freeze the weights and biases. What do? You still do the forward pass, but you don't take the gradient with respect to the loss. You instead take the gradient with respect to the output. And you need not take the softmax output in case it's a classification problem. You can take the one just before it, just the raw score, because softmax doesn't add any value to you. So you can do that, but output roughly conceptually. And you take its gradient and you start back propagating the gradient with respect to, and till it will back propagate with respect to the weights. But finally it stops because there are no more weights, but you force it to go even further, one step further, to take the gradient with respect to the inputs. And so you come up with the sensitivity of the output with respect to the input. Just a little bit of code, and then you are able to do that. And that helps you create this beautiful saliency maps. And then there is the activation maps. The activation map thinking is like in a ConvNet, you take the last layer and then you basically say that I'm getting certain values. Now, if I, like at any given, what is this filter? What is this feature map trying to tell me? How would I find out? One way that you could do it is you could just shake up the inputs, right? To figure out that where, if you, this particular feature is looking out for what in the input image, right? And so forth. So there are all of these different ideas that you can do. We talked a little bit about the deconvolation and so on and so forth. I won't go into that anymore. We have covered all of that. We talked about the occlusion-based methods, and we'll do that in the lab. We took the example of the lung pleurisy, I believe, is the filling of the fluid, where we have a very clear angle that the physicians look for. And if they don't find the clear angle, as in this picture in the left lung, it gets blunted or it becomes smoother, then they know that there is a filling of water or fluids in the lungs. So then the question is, what does the neural network look at? Surprisingly, it turns out that neural networks, well trained, learn exactly the same thing. They manage to understand that feature and zero into it. You can do it through saliency maps, you can do it through this, that, and you can do better still. You could do by occlusion studies, right? Or ablation studies. You just remove little pieces of the image and see how much your performance or your score degrades, and prediction score degrades. Right? So that is it. So with that being there, that's a review, guys. Should we now make progress towards the lab, guys?
Yes.
Let's get to the lab now. And
mine is kind of hanging on that, plotting the individual tree just before the Shapley, the SHAP library.
Oh, that tree, it takes a long time to draw. It's a very busy. So it's not your laptop, it's just the nature of the beast. So guys, I'll start by showing you a simple situation. Let's go to the California data set, simply because you have all done the California data set, isn't it? Right. And let me do this. In the California data set, if you remember, like, is the font reasonably, okay, sorry, it became too small.
Yes.
Is this good enough, or I should make it bigger?
Make it slightly bigger.
Slightly bigger, huh? Okay. On my machine, it's looking, on my screen, 50-inch screen, it's looking huge.
It looks decent on my, I'm not sure how many inches.
Okay.
One thing I find useful is that when I get a new notebook, it's got all the nice output of it working.
Yes.
I do a download as HTML.
Yes.
So I know how it's supposed to look before I start trying to run it and have specific environment issues in my machine.
Yes.
So.
Nice. All right, guys. So I'll start with the California data set. Just to whet your recollection, you have done this in your past. Anybody remembers doing the California data set for regression?
Yes.
Yes.
We all did that, isn't it? So this is that. So let's go and add Shapely to it. So if you remember, we loaded the data, then you visualize the data. But at the end of it, I won't go through the bulk of the analysis because you, by now, it's become almost a textbook case. Everybody knows what we did. You do the missing value analysis, you do, and I won't go into it. You can use the profile, this thing, to get a profile report. Let's move past that. You can do correlation studies and all of that. At the end of it, you can draw it upon a map, and this is your, just to visualize the data. This is your data, okay? By different factors. And this is it, just to give you a visual reminder that this was the data. Housing data, house prices. And the house prices seem to depend on 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 features, like 10th being, of course, the target variable, the median house value. You have to predict how much is the median house value in a block, in a city block or a street block. So if you remember, the data showed a pronounced skew. If you get better models if you address the skew. So this was your heat plot and so forth. Right. Then correlations and so forth. So all of that I'll skip. So data pre-processing. The first thing is you have a categorical variable, namely the ocean proximity. So we need to do one-hot encoding. This is doing the one-hot encoding. But something else, because we saw pronounced skew in some of the features, what do? We take the log transform of it to see if it makes it better. And when you do the log transform, the situation certainly becomes better. The skew is pronounced skew disappears from those features, which is a good thing because, as we know, and we experimented and we found out that it does improve the quality of the models that you build with it. So I will go ahead with it and I'll go straight to one of the models, random forest. We built a random forest model which seemed to have, what was it? A coefficient of determination of here, 84%, give or take. Now the question is, once you have this model, right, and we realized that in every way it looked good, the residual plots looked good, the error plot looked good. And by the way, this is this very, very complex tree that you're trying to visualize, Kate. It's hopeless almost. Okay. So the thing is, random forest, people often use it for feature importance. And what I'm trying to tell you is, no, don't. It's misleading, actually. It's the mathematicians have written fairly detailed articles why it's a bad idea. Rather, you shouldn't trust it. Right? Sometimes it works out, it happens to be correct. Quite often it happens to be correct, I would say, but it may crucially fail. So go with the gold standard, go with things like Shapely line, etc. Right? So what would Shapely do? First, we install Shapely. So here is the installation of the Shapely. Now, Shapely comes with two basic explainers. Remember, explainers are in some sense local models or sort of that you can build. And then you can play this game of what is happening. So you create data from the f function, and then you try to explain it with a surrogate function and so forth. So there's a tree explainer which works very well with the with models when you're trying to do a surrogate for tree-based models like tree, decision tree, random forest, XGBoost, etc. These things work well. But there is another kernel explainer which works for all other situations, and you can apply to neural networks, and you can apply to anything. So the equivalent of what this feature importance is, you can get from Shapely, and then you can see if they match or not. And they sort of seem to match median income, ocean proximity, latitude, longitude. Proximity, latitude, longitude. Then comes population, total rooms, total bedrooms. Population, total rooms. Oh, the order has changed here. House, median, age has turned out to be a little bit more important. So anyway, this is it. But this is, again, a global, very rough and ready measure. You shouldn't look at that. What happens if we look at the value for some particular data instance, right? We just take a particular row of data randomly here. You take a row of data and then you say, okay, we are going to do the feature importance for this row. It happens to be 160th row of data. So every time you run it, it might pick up something else. Or maybe because I did random seed, so it might do the same thing. Now, this is a plot. It is called a force plot. So do you see, this is actually, I find this to be very, very useful. And there is a lot going on here. So let me explain what exactly is going on here. Sorry, let me first increase the font actually, not decrease the size. Even more. Oh, where did I go? Oh. Yes, let's go here. Are we able to see it, guys? So the FX, the median house price after taking the log transform. So obviously it becomes a little opaque because I took the log transform of things. So it's 13, right? So you can think that e to the power 13 would be whatever it is. That's the median house price, or the, not median, average house price, expectation value of the median house value. Right? So that is 13. Now the question is, what are the forces that are moving it here and there? For this point, the prediction is, what is the prediction? We'll have to see, okay, I forgot to make the prediction for it. That would be, let's say, illustrative thing, I forgot. You just make a prediction on this. Now the question is, what factors are affecting it? So here it is saying that, and it does seem like that median income is a positive force. Do you see that it's red in color? And it is pushing the value higher. Means if the median at this house price or in this particular local market or segment, the more the median income of people living around you, the more the house value. Right? And median income seems to be the biggest sort of the positive force. On the other hand, the biggest negative force seems to be, what can you guess, guys? What does it say?
The age.
Yes, the median age of the houses in that block. In other words, how old is that neighborhood? It turns out that in this particular place, the older the neighborhood, it has a negative effect. So it begins to push it down for you. Then proximity to ocean, ocean proximity inland. So it basically say that wherever this is, if the house is inland, strangely enough, in this particular price segment, it pushes the value of the house up, right? Then longitude and latitude. Well, if you ever talk to a real estate agent, you know, what do they say? That there are only 3 factors that matter in real estate value: location, location, location. Well, it turns out that they would be surprised if they saw this, because here it's not just the location, it is the latitude and, I mean, it's the location. Location comes after, well, sort of ocean proximity is location related, after income, median income, right? Then the location factors come. So the red are arrows that pushing it up. They're saying that these factors here locally have a positive correlation. Are we together? To house price. And the age has a negative correlation. And it need not be always true. And as I will show you, for a different point, we will come to a different conclusion. So now what happens is, here is this plot, which is...
So Asif, where is age? I don't see that age there. Oh, the blue, okay.
You have to hover over it. If you have an HTML copy, you can too.
Yeah. So now this one, sample by similarity, you get, you know, you can pick the values. This is something very interesting, actually. These are called force plots. There is a lot going on here. It is nothing but, see here, it is for one target value, right? A house price value, right? And it is with respect to sorry, I take that back. Hang on. When I was explaining, I made a slight mistake. The base value, the average value log transformed is 12.08, right? This house seems to be at 1305. This data point that we took, the median house value, is higher than the average. Why is it higher? Because it turns out that the income seems to be contributing to it. It seems to be a slightly wealthier group of people, right? And location seems to matter, right? So always look at the base value and compare it to the value here, the value of this data point. And then ask this question, so which factors had positive influence? Which factors have negative influence at that moment, right? So the next is force plot. So now this is for one data point. What if I could take all the data points, right? And there are, I believe, 10,000 or more data points, say 11,000 data points. And for each of them, there would be a certain Shapley value. And what I do is so you notice that the value is, fx is here. This is the value of the house. And the x-axis is the Shapley value. How big is the Shapley value? So obviously, at this point, the Shapley value seems to be a pretty, like, factors seem to have median income, ocean. Obviously, every time it comes to the same thing, income. And, housing data is in some sense a simple data. But if you look at it, you can change it to other things. For example, you can change the axis, by the way. This graph has a lot going to it. You can say a similarity or by population, right? So as population increases, what does it do to the house value? So let us see. In fairly low population areas, it seems to have a positive effect, right? And the factors that are impacting, look at this, population seems to have a positive effect, right? And it always seems to have a positive effect from what I can make out. The more populated a place, the more the house value. So, well, let's take something that may have a different interpretation.
The ocean proximity is nice and simple. That's a whole lot of plots in one. It's a fascinating dynamic plot.
Yes. Yeah, this is it. So what does this say? The ocean, if you look at the ocean proximity, the closer to the ocean you are, the more the value, the more it pushes up the house value. So would you say that it is true?
Yeah, it's one of the most straightforward plots.
Yeah, that's right. So total number of rooms. Well, it turns out that the total number of rooms has a different sort of it's not very obvious how it is doing, but essentially it's a force for the good, it seems to. So longitude, latitude. So anyway, it turns out that for different values of the number of rooms, is still the contributions, the Shapley contributions are determined by pretty much the usual suspects. Right? So anyway, this is called the force plot, and there are more plots. There's a partial dependency plot, which I didn't do. So we will go through the documentation for Shapley, Shep package, and I'll walk you through more features. Now, I have a homework for you. I didn't do the partial dependency plot. It's very easy, couple of lines. Do that. There are a couple of more plots in the Shep package. Read the documentation and become familiar with it and use it. See guys, the most important plot is this plot. If you can understand it and also realize that, see, feature importance as a global factor is a very rough and ready measure. Don't trust it. Feature importances are much more sensible locally because a highly complex manifold, the curvature in any of the dimensions keeps varying all over the place. So feature importances are changing all over the place, right? And so go local and look at what is happening around the data point that you care about. Right? So the same thing we do it with, I think I've repeated it with what have I repeated it with? Support vector machines also I did it with, I think. Did I do it with feature importance? With which is it? No, this is for the tree. Now, let's see, goodness, effect measure, predicted error. Yeah. Oh, this is, by the way, a very important plot that I forgot to mention. So I've done it in the support vector thing. Guys, 1 second. I'll entertain the question in a minute. If you don't mind, is it okay if I just explain this before we take questions?
Sure, sure.
Yeah, just a thing. So this is actually very important factor, guys. If you ever want to look at just global influence, trust this picture more. What it is showing you are all these features, and this is the Shapley value, 0. See, it is the absolute value that matters, not positive or negative. I mean, they exert force in the positive or negative direction. That is all right. Now, this is the feature value. So what it is saying is that the low latitudes seem to boost up. It turns out that they seem to boost up the house price values. Can you guess why that is in California?
Is it like near the ocean?
It will be with
latitude. My interpretation for this is actually that it is San Francisco Bay Area tends to be fairly expensive. So it has produced. And the other thing also is true. So compared to the median, see what is in the center, the Central Valley, right? So low latitude and high latitude are probably, this is Los Angeles and this is probably San Francisco Bay Area, right? And they both have a strong impact on the median house price, right? So that is that. Longitude is the vertical lines on the globe. Here also, you notice that they seem to have 2 clusters. The 2 clusters probably correspond to the LA area and the San Francisco Bay Area, because if you notice, the state is along a diagonal. I don't know if you will go back and look at the data. So that's the interpretation that I can think of. Yeah. Let's go back to the map. Yeah. So look at this, guys. If you look at this graph, do you notice that the San Francisco Bay Area and Los Angeles, these are 2 population centers. They differ in latitude and longitude, both, because it's the California state is a diagonal. Do you see that, guys? Right? And so you expect sort of 2 clusters when you see that map. Yeah, this map. So let's see what factors don't seem to matter too much. It turns out that total bedroom seems to have not that much of an impact. Do you see that? If you have high number of bedrooms, low number of bedrooms, still doesn't seem to have much of an impact. So what happens if it is red and on the right-hand side? So if it is red and on the right-hand side, like for example, this, what do you think it matters? It means that the bigger the more red means high value, right? That feature has high value. High median income leads to, it is a positive indicator of house price. Does it agree with common sense, guys?
Yes.
That's right. So that is what this is saying. Similarly, let's look at this other thing. I don't know, total number of bedrooms, it seems to have a positive correlation. Number of households, I suppose it's a measure of how densely populated it is. But sometimes some things look a little odd. The population, low population seems to have a very strong impact on the Shapley value. I am thinking how that came about. And low population, okay, this is high population. High population seems to have, do you notice that it's the other way around? It has a negative Shapley value. I am guessing that it's because these are apartment livings. Like in a block, if too many people live, those are probably apartments. That's sort of the interpretation I could come up with. Isn't it? Like, for example, the freestanding homes in a block, there wouldn't be too many homes, but in a apartment complex, there would be a lot of homes in a given block.
Asif sir, so the value is increasing in x-axis of the feature, right?
No. The feature value is by color. Blue is low, red is high.
Correct. That's for the shapely value.
No, not the shapely value, feature value. So whichever feature you're looking at. So suppose you're looking at population. Red stands for high population data.
I see.
Blue stands for low population data. Right? Okay. So here you seem to have an inverse correlation, which probably should agree with our when we did the data exploratory data analysis. We must have done that. Let's go to the exploratory data analysis and confirm whether that was actually true in the data. It must have been true. There must be, okay, here we go. So we are saying median house value and population. Yeah, do you notice that it's slightly, it is not blue, it is more on the mellow red side, isn't it? You see this population versus median house value, where my mouse is?
Right.
It is slightly negative correlation. Right? Okay. So that is, so that seems to be borne out by what this model is saying. So guys, this is it, you know, these shapely, these graphs that come out, you have to spend a lot of time because a lot is packed into each graph. It's explaining a lot actually. So you have to become.
Asif, a quick context question, like at Cornerstone, an exercise like this, would it be the data scientist or would it be the domain specialist? Who participates in this exercise?
See, typically, our situation is different. We talk to, like, see, the problem is, for example, suppose I am looking at, okay, let me take an example, recruiter efficiency, right? Recruiters, so the reality is a company gets gazillions of resumes these days, right? We live in a dumbbell economy, which means that the entry-level jobs are extremely hard to get. Actually, any given day, it's much easier to find a job, in my opinion, as a VP than to find an entry-level job. Because gazillions of resumes come for some of the common, you know, mainstream jobs. The recruiter, here's a dirty little secret, and I know it from one of the biggest recruiting houses. Most places, recruiters don't read all the resumes. What they do is they have some computer system and they just do keyword search. You've seen, you know, index, text search. Pull up a few resumes, and from the resumes, if some looks good, you barely give like 2-3 seconds, 5 seconds to a resume. That's all. Not even a minute, just 5 seconds to decide, oh, you know, do I want to look at it more carefully? You take a small bunch of resumes, you reach out to those people and you say, all right, let's have an interview. So a tremendous amount of resumes don't get looked at and so forth. So one of the things that I'm looking at is what factors are there in the resume that makes it more worthy to look at, because every single company is losing out gems. For every great guy they hire, they probably miss 10 great guys who have applied but got ignored. It's happening. Right? And the fact is, so remember that when you apply to one of these big boxes and you don't hear back from them, or you get a very rough treatment, it may not be you. In fact, most likely it is not you. It is just that they are overwhelmed. Right? So one of the questions is, how do you determine, based on all the factors of an applicant, what factors are most likely to indicate a person of interest, a person who is worth interviewing, or you should prioritize interview with. So that is one way of using Shapely. The other way, in my case, when I was doing that early work in the startup, it was the happiness. Happiness is very direct. You have 200 factors. How much do each factors matter? You realize that is the central question, right? And that central question you're not making a prediction. You're asking a very human question. How much does each factor matter with respect to, let's say, attrition or productivity. Those are all indicators of happiness in some sense, quantitative indicators of happiness. So there it is shapely. Right? So who does it? You sit with the domain experts to find what factors may be implicated. Then you bring in those features. The shapely analysis you do. And then you go back and show to the domain experts that, see, this is what our data shows.
And what I sensed was the kind of thinking that goes behind using a package like Shapely is a little bit of a higher level thinking. You need to know something about the analytics of what you're working with. But if you don't have a good awareness of the domain, the insights don't speak to you.
Yeah, see, ultimately, right, you cannot extract information where there is no information. The purpose of AI is to squeeze the lemon to get all the juice out of it, right? But the lemon better be juicy. In other words, you better bring in data that actually has the relevant entropy, the relevant information. If it doesn't have, no amount of AI will squeeze anything out of it. You can't squeeze water from stone, kind of a metaphor comes to mind. Right? So once, whatever forces are there, you can do a Shapely and see how those factors are affecting. See, this sort of analysis, interpretability, to me is quite central. I care a lot about. I feel that every developer should know about it. And because it looks complex and hard to explain to people, you don't find it in typical, the machine learning books. These things explain very much. Though I would say that increasingly it is being noticed, right? Lime and Shapely, etc. They will gradually become mainstream, but they are not yet mainstream.
Because this is very powerful. Like this is how AI can be put to work.
Yes.
Right. To get the buy-in from an exec, you need to be able to substantiate.
Yes, and this is the substantiation. This is the way to make a case for things. These things are very real impact, very, very real impact. Right. So once again, you can do, so now let's look at another data point. So with support vector machines, I took another data point. So, okay, this is, now you understand this and you understand the force graph and you do this. So I think, yes, go ahead.
Because I was stuck with a question in the previous plot. So when you plotted the one, you had 1,000 or 100 samples put into the Shapely, and it generates this plot, right? If I'm right.
Yeah, I'll tell you what happens. This computation is a little bit brutal. Mm-hmm. I had to prepare this notebook quickly, right? Mm-hmm. I didn't want my notebook to hang for half an hour. So I just sampled the data.
Got it. I see. So yeah. I see. It didn't work on the whole set of data, but a sample data.
Yeah.
And then it drew its conclusions.
That's right. I just took a random sample of the data.
Okay.
So 1,000 points. Imagine finding the feature importance. It is almost useless, no? Because do you really need to find all these points that look very, very similar? Do you need to do feature importance for each of them? Because you know that it will be pretty similar in the neighborhoods because they are all in each other's neighborhood. Yeah?
Got it. So Asif, the reason I'm asking this question is, this is Shapely on a regression model. There is other model that we look at mostly like a picture, like a 200 cross 200 picture, and takes only one picture and then puts the bright red spots on the place that led to this particular class being predicted.
Yeah, we'll come to
that.
The lab.
Okay, got it. Okay.
We'll do it shortly. Yeah? So I wanted, let's crawl before we walk kind of thing. Yeah? So this was an exercise more in just getting you familiar with the thing. And now that you understand Shapely, understanding it, explaining it with image, all this force graphs is a bit harder. Like here, when I explain in terms of concrete variables, median income, etc., it's more sort of easy to understand. But I'm coming to images. So this was Shapely, and oh my goodness, I'm running behind in time once again, guys. So guys, is it okay if I go slow and make sure you understand, or we should go a little bit faster?
It's okay. Finally plotted that tree. It took 48 minutes. Plunging into the SHAP stuff now.
Yeah. Yes. Have fun. And before you know it, I seem to be almost making a sales pitch for hardware companies, isn't it? Buy expensive hardware to make it run faster, all of this. Anyway, so I'll take this. So I didn't take too many examples because the SHAP documentation, if you go to SHAP, read the docs.io, all of these links are there on our page. And I'll also put it on Slack, copy paste it on Slack. It has a lot of lovely examples, right? We're going to look at some examples, and let's look at, I don't know. If you look at, okay, this is, I need to increase the font. This is on image data set. So what makes you decide, see, you realize that they're positions. So let me explain. This graph is a bit hard to understand. This is the MNIST data set. So how many digits are there?
10 digits.
Well, digits are 0 through 9, but there it just shows.
So that is the index. Imagine that horizontally. So forget the dark black. Dark black is the input. Each of these horizontal columns is placed for one of the digits. So this is the place for 0, and this is the place therefore for 9. All right. So when you give it digit 2, it seems to go for this. And do you notice where is it putting the feature importance? It is not
over all of it.
Exactly. So in fact, it is telling you something negative. It is very clearly saying it's not 3. If you know the shape of 3, this, I don't know, it's a little hard to explain. Let me expand it a little more. Where am I? Okay, so all right, let me start from here. Not the image plots. Think about this. Do you see this little bit of blue? Yeah. Would you agree that if it was 3, because this is the location for 3, that's exactly where you should not find ink for a 3, right? Sort of, you wouldn't want to find ink there, right? So things like that, you get the negative impression. And for where do you expect the positive impression to be? See, for 2, it is in the location of 2, it's paying a lot of attention to this shape, right? So that is what it is trying to say. Where is it paying attention to? For 1, of course, it's paying attention, right? So what you can't make out is the fact that it's a square pixel. So in the whole square pixel, for 1, it seems to pay attention to literally the center, the vertical line, isn't it? You can, if you look at the attention, where it is like which features or which pixels it is giving importance to, they're almost the shape of 1, isn't it, guys? This is almost the shape of 2. This is almost the shape of 0. And this is almost the shape of 4. And as we use other techniques, you'll see that we'll be able to recover pretty similar results.
So you can see for the 4 and the 9 on the far bottom right, that blue line saying, well, there's no line there, so it has to be a 4 instead of a 9, right?
Exactly. So it is paying attention here and saying, oh, there is a gap. And by the way, here, this is missing, right? And therefore, this is a 4. Right? So, this is it. You can have a lot of fun. I won't go into a lot of this. You can have a lot of fun when you do the text data. And you see, for example, if you're doing sentiment analysis, the very basic thing, let's take an example. I think, yeah, auto tokenizer. This is obviously the Hugging Faces, right? Which you are all familiar with, hopefully by now. So you're giving it data, like this text is angry, this text is happy, sad, etc., etc. You ask this Shapely to explain it. So what is it doing? It is saying that, well, this and the thing. And so it is coming up with features, funny, has a positive, nice. This is it. Faced with tears of joy. It sort of latched onto some, I don't know what it was doing here. So I would ignore that. Funny, nice, haha, law. These are positive correlation. Even lost to give positive correlation. Beaming face with smiling eyes, right? It gave positive. things, you can ask it, what are the top negative features? What makes it give you negative answers, right? Then look at that stupid, crying face, sad robot. Oh, India seems to have a negative impact. That's sad. Top words towards sad emotion, pain, crying, sad. You see how well these things work, guys. Huh? This is computationally a bit expensive. Shapely, as you will realize when you do the lab, is expensive, but it's really worth it if you have the time to do it.
I think, sir, the other one, the one about this, where it was the one about this, sir, the top negative words for positive emotion. The one above. Can you scroll up a little bit?
Yeah, this one.
Yes, here it says the top negative words. No. The one where India was there, sir.
India was there. Top negative words towards emotion happy.
Yes. So even these are negative words, but they represent the positive emotion, looks like.
Oh, they represent the positive emotion. Interesting. Crying face, sad robot. Perhaps. So this is it. I mean, you can, the point that I'm doing is these are fairly versatile tools that you can apply to.
So Asif, this is where the question actually came to my mind, both in the image as well as in the NLP. You're just giving one sample and then it does the extraction of the feature importance.
The reason is you've already trained the model. You're giving it a model and saying, explain this model's prediction for this sample and explain why it is saying what it is. That's the way to put the context. The context is, I have a data point. Model has made a prediction. And you're saying, okay, here is the data point. Here is the model. Explain to me, why did this model make this prediction here? That is the problem.
I see. So still a game theory is being used here to build.
Of course, because you can perturb and generate a lot of data around it and go about playing games. Right?
Got it. Okay. Got it. Okay. Okay.
So, yeah.
Yes. If we assume there is no limitation on the hardware computational power, then can we say that Shapley is better than the the first method where we were trying to basically create simpler model on the local neighborhood?
See, generally, right, in some sense, SHAP is considered a superset of line, right? It is considered a superset. It subsumes line, but Lime is cheaper and faster.
Right.
So it depends on the time that you have. You want to do Lime, like for example, I always start with Lime. Even though I know that Shapely will subsume it, I'll start with Lime.
Got it. Thank you.
So this is it, guys. See, do you notice that for words, for each of the sentences, the problem affecting people using older versions of the PlayStation 3. So this is a blah, blah, blah. It is attaching, it's telling you where words matter, which words matter positively, which matter. So I won't go into more of it because we have a lot of territory to cover, but I hope you got the sense of Shapely, isn't it, guys? And the SHAP thing. It works for everything. Actually, one thing that I like for, I don't know, it's a little bit, yeah, Patrick and Sipal. Either of you are here today? Sipal, you are here. Patrick, where's Patrick?
Yes, sir.
Patrick isn't here. Okay, you like this example.
Okay.
So you're familiar with genomic data, isn't it?
Mm-hmm.
Yeah, these days, by the way, I'm researching genomic data at this particular moment. So in a different research project. So look at this course. So when you have seen the gene sequences, right? It is telling you which part of the gene sequence matters. Do you see? Are highly important.
Yes, sir.
Right? Isn't it amazing?
Yeah.
Right? Exactly for this situation, what matters. I find that so lovely, just to see this. In the long genomic sequence, oh, pay attention here, 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 and so forth. Do something. So a lot of things are here, guys. Tabular data example. They have other examples of tabular data using all sorts of things. So we can literally go gaga over it. You can do the diabetes. Oh, yeah. So iris, I'll take. Let me show iris because I'm going to use iris for the next example for line. So this is iris, right? If you do. So suppose you take the simplest model, k-nearest neighborhood-based method. What it is telling you that there is some data point whose the average base value is 0.35. This thing's value is less than that. It's 0. It seems that less than 0. So it is pushing it hugely in the negative direction, because it turns out that the petal, sorry, this is the overall, I don't know, what is this overall value? I think, what is the target variable they have taken? Let's go and look at it. Data split, iris, accuracy, format, okay, kernel, k-nearest neighbor, explain, expected value, shape value, I location. So it is saying that in explaining this data point, the most important factor was petal length. And because the petal length was short, it pretty much could decide for that. And this is pretty much giving you an idea. So by the way, does this make sense? If you know the iris data, keep this picture in your mind. The reason I'm saying it is, it has a meaning to it. The output value is here. The output value is actually 0 to 0, 1, 2, 3. So it not, yeah. Suppose you say the effects, this, but anyway, these things will remain the same. Keep these things in mind because I want to show you something in a little bit. Right? Support vectors. So anyway, you can apply all sorts of models to it. Let me take a more different example rather than this. This is too simple. Iris classification. Diabetes. Diabetes is more interesting. Let's go there. So diabetes data set, as you know, it's one of the standard data sets. So here, the target variable, I don't remember what it was. It was, anybody remembers what was the target variable in the diabetes data set? We can look it up quickly. Was it the sugar level or something? It seems to be almost the sugar level, isn't it? So what? This looks like the sugar level, right? Sometimes I do run this if I'm not careful. Yeah. Yeah. So it is, so okay, let's assume that it is that. Huh? I should have done due diligence and seen what the target variable is. So look at this. Base value is 151 in this group. Obviously, you're looking at people who have diabetes. You're saying that if this particular patient seems to have this value, what are the factors that are giving huge contributions? BMI. Would you agree that BMI is a significant contributor to type 2 diabetes? The bigger the BMI, the more likely you are to have type 2 diabetes.
Yeah.
Right? What is the first advice that doctors give you the moment they notice you are bordering or you're getting into type 2 diabetes territory? The only one thing, reduce your BMI, lose weight. Then sex is a negative factor. My guess is that here it is taken as a number and women have been put 0 and men have been put 1 because women have a lower incidence of diabetes from what I remember. These blood pressure seems to have a positive impact. Does that make sense, guys?
Yeah, blood pressure is not good either.
That's right. And so we can see those values because it's a little opaque. I don't know what S1, S5, etc. It's a little hard to tell. And what you see is that, again, you get a map. So what things have so looking at this, let's look at what things have a direct positive correlation with Shapley values. Red and to the right, BMI. You see how important BMI is. Also this S5, whatever factor that is, right? And blood pressure, get your blood pressure in order, right? And I suppose this is not actionable, but it's basically saying women are likely to have a better outcome. So, well, that's that. I don't know how the gender is specified. I've forgotten this data set, actually. I haven't seen it in a long time. But it sort of makes sense, isn't it, guys? Yeah. And then you have a dependency plot. What is a dependency plot? You take the BMI of people and you ask this question. So suppose you ask this question. See, I know that BMI is important, but what is the most important context of BMI? See, two people who are 30 pounds overweight, one of them is 30 and one of them is 50. Who is more likely to have diabetes?
The older.
The older one, right? So this thing has picked on to the fact that when you talk of BMI, it interacts most, given all other factors, it interacts most with age. So it is the coming together of BMI and age that sort of determines the impact. And one thing you notice, the BMI has almost a linear relationship with the Shapley value. You see that, right? As you increase the BMI over the average, so this is with respect to the average, I'm guessing, your Shapley value begins to keep climbing up. But at the same time, they have color coded it by saying, look at the age. You notice that these places, there are still some blue, low age people with very high BMI. I suppose in this particular community, there were young and obese people. That's very interesting. You seem to see a pretty interesting age distribution with respect to the BMI. I didn't expect that. So Paul, does it make sense? Forget the Shapley value. Just look at the BMI and the color of this age. Is this something medically that you guys see, that the BMIs are now pretty like spread out over all age groups?
Yes, sir. If you're, doesn't matter if you're eating much, you know.
Yeah, whatever your age, you'll
You're chubby kid, then your BMI is high.
Right, yeah, that's true. Makes sense. Well, guys, here is the force plot. Yeah. So at each value of the output here, you can see that if I'm looking at, let's say, 41 or 40, like you can just go up and down and you can see what is going on at this particular level, what matters most. So what is the thing having the most strong positive impact? Sex, BMI, and S1, whatever that is, the one that is pushing it down here, BP here in this particular range, BP and so forth. Right? Now, the high impact areas at this moment, if you're very, very heavy, you realize that, do you notice that this graph is trending upwards? Right. In other words, high impact or high Shapley values happen when you're rather plump. Then almost all the factors seem to contribute quite a bit. This thing is mostly red, whereas for very low impact areas are generally for relatively lower weights here. Anyway, so you can play around with it, guys. You know, these things you have to sit and think a lot about and come up with that. And this again shows that BMI, if you force it to have a Shapley, here it is engaging with S5. Why are they? Okay, the decision tree is coming up with a slightly different plot, it seems. Right. So that is that, guys. And so enough of Shapley. Let's move on to the next one, which is, and by the way, this is the package. If you want to go to GitHub and download it and so forth, this is the package. All you have to do is pip install SHAP, that's it. And the example on the GitHub itself is very well explained. Okay. One good thing with Shapley is the quality of the documentation. Absolutely lovely. Now let's move to line. So before I go to the more complicated examples, let me go back to the notebook that we were dealing with. Where is that notebook gone? XAI, my simple notebook. Let's start with simpler. Oh, by the way, Balaji, thank you for pointing me to Captain. I was going to
Captain. Yeah, that's what we are actually moving to.
Oh, okay. Yeah, so I'll also move to that. Actually, I didn't realize this. I was using Flash Torch and something else it was my team was using. I forget what. So, so here's the thing, guys. Think of Okay, so you guys have a homework. This line, I'm doing it for Iris. And because you know we did Shapely for the housing data set, I leave that as a homework for you. Right. So now let's look at Lime. Lime also is very easy to install. Just give this command, it will install Lime. Do I need to explain this line, guys? What does this line do? What does this cell do? Loads the data and does what?
Splits into train test.
Exactly. And then this builds the model and predicts it. So obviously I haven't put explanatory comments because I assume that by now this stuff has become kindergarten for you. You get an accuracy score. Oh, goodness grief. This has come up with a perfect score. No, it shouldn't be like that. Let's run it again and hope it's not perfect this time. Yeah, better, 94%. Good. 94, 95%. Iris is a very simple data set, of course, you expect. So what I'm doing is I'm taking a random row and saying, explain this row. And when you ask it to explain this row, it says, if you look at this row, by the way, this is sepal length, sepal width, petal length, petal width. And what is not obvious from here is that the petal length and petal width are actually small, relatively small. Right? Because if you look at the picture, you'll realize that petal length and petal width, what is the average? It's about, let's say 1.5 give or take for petal width.
Is
and
this
for
the lab
petal,
you were given earlier or now?
Come again?
Is this I only saw the housing notebook.
Oh, this is a different notebook. This is the I'm giving it to you, XAI notebook. This is the Iris dataset. So Iris dataset you're familiar with, right, guys? This is the distribution on the Iris dataset. So what is the average value of the petal length? It's around 4, give or take, isn't it? Look at this. The scale goes from 1 to 7, so probably 4. And petal width, it is about 1.5. So relatively speaking, you have gotten a data point whose values, petal length and petal width, are very small, isn't it, guys? Does that make sense?
Right, there were like 3 clusters. Two of the clusters are close to each other, if I remember.
Yeah, that's right. We'll come to that. But I want you to pay attention to the fact that in the Iris data set, at this particular moment, the average petal length is about 4 and average petal width is around 1.5. And whereas here, the average petal length is 1.3, way below normal, and average petal width is also 0.2, way below 1.5 approximately. Right? And so the prediction from this model is that it belongs to the 0 class. 0 class is the Cetona. There are 3 classes, Cetona, Versicolor, and Virginica. Right? 0, 1, 2. And in this graph, 0 is marked as red. So let's go and look at this diagram. And I want you guys to pay attention to this diagram. These diagrams are the same diagram, diagonally, right? Petal width. In other words, they're just rotated versions of it in which the axes have been reversed. So here, what do you notice about Cetona? The petal length and petal width are very small, isn't it?
Yes.
Right? So if you have to find Cetona, look around. So think about the factors that will individually help you decide what is relevant. Can I look at this and tell that I should use sepal length, sepal width to decide between the two? Probably not. It's not a clear distinction. This one, maybe I could use sepal length and petal length, potentially. But then I'll get a mixture here, right? If you really think about it, of all of these, the cleanest is this. Do you realize that? Both along horizontal and vertical axes, you can create a box. You can draw a horizontal line here, and you can draw a vertical line here, and the red ones, the Cetonas, are well separated out. So just looking at this figure, you know that if it is Cetona, the single most important factor would be petal length and petal width. Are we understanding this explanation, guys?
Yes.
Just look at that, right? And now let's see, what is it saying? Oh, it's saying that its prediction probability, it is very, very sure that it is Sedona. And why is it Sedona? Because the length of this is very small. It is much smaller than these values, right? And the feature values are 1.4 in this. This is the value that you find here. And it is much smaller than that, basically, right? So it latched onto the truth. It latched onto the fact that these are the two features that most matter, right? So here we see the average values are 4 and 1.5, and this guy is like, yeah, okay. So what happens now, suppose I force the force set. If you believe that petal length and petal width are most important, then would it be fair to say that if I exaggerate the petal length and petal width, it won't be Sedona anymore? What is it? Sedona. It won't be Sitosa, sorry. What am I saying? I went and stayed in Sedona, so I keep confusing this with that. Sitosa, sorry. I think I've been saying
what you meant.
But not. All right, so you realize that if I boost it up, I will be here, isn't it? If I increase the petal length and petal width, I'll be somewhere here. And I clearly won't be a Sitosa. Make sense, guys? So that's what I do. Let's see what happens. I deliberately, in the same sample, I exaggerate the petal length and petal width by hand. Do you see me that? The line 62, is it self-explanatory, guys?
Yes.
Yeah, you do that. And when you do that, immediately it says it's 83% sure it's a versicolor, right? Which, by the way, this green here is the versicolor. Right. So it seems to have guessed it properly. And you ask it what matters now, it again says petal length and petal width. Let's see if that makes sense. Yeah, here. Still, it seems to be. It is not so well separated, but petal length and petal width are still, if you look at the other figures, between them is still the best separator. Right. So if you really look at this figure, you realize that globally, this tends to be a pretty good way of looking at it. So this is it. Now install Captum, you have to just give this command. I'll go to the Captum website to show you. So guys, are you understanding line? Was that easy?
Yes, sir.
Yeah, straight. So now let's go. By the way, I'm not giving you guys a break. I apologize for that. Let's go ahead and finish. The next thing we'll do is Captum. Okay. So Captum models. So pre-train, let me take some good examples. Okay, this is a good example. Or this is an example I have taken straight from there. I just downloaded it into my local just so that I could show it to you in big fonts and give you the commentary along with it. So Captum is very well integrated with PyTorch, and thanks to Balaji for introducing me to it. So I've just been playing around with it in the last few hours, one day. So let's look at this. Guys, does this code look all like by now worth yawning at? This is obvious code, right? Remember image processing, these were the transforms, these were the normalizations, and so on and so forth. And then you take ResNet, you take a picture, swan, right? The name suggests it's a swan. You take the transformed image, you do all of the usual things we do in image processing. Just go back to your very, very first homework. You'll remember that. Now you have a model. ResNet is already able to do things. We are going and we ask it to predict what is it. And it says that it has a 46% chance that it is a swan. It is a goose, right? Now the question is, why is it calling it a goose? Let's go find out. So this is, you use integrated gradient. Remember, gradient is the same thing that I taught you about, taking the derivative, the gradients, and probably looking at that. A sophisticated version of that. You do a little bit more, but pretty much it. So this goose, when you ask it to create the map for you, gradient map, see what it has done. Look at this picture a little carefully, guys. Do you see something like a bird here? How many of you can see the outlines of a bird? The darker points are the points with greater gradients, assume
It's
that.
like its beak is pointing toward the right, as
Right.
kind of ostrich-like body.
Isn't it? It is, right? So it knows, it is able to recognize that this is not a house, this is not a ball, this is not a one of the many things, aeroplane, and all the gazillions of things that are there in the ImageNet data sets and all that. But it happens to be a bird, right? And how did it? So then you can do some further noise filtering and so forth. So there's a bit of technology, guys. Huh? So you play with the derivatives, you set to null, you smooth, you do this and that. And now the same picture, you improve upon it a little bit. And now what does it look like, guys? You look at this picture and suppose you had not seen the left one, you just see the right one. This is what the neural network is paying attention to. Does it, I mean, would it begin to look like a bird to you?
Yes.
Already?
Yes.
Pointillism.
Yeah, pretty close to it. And see what this is the image. So you notice something very interesting. It has latched onto the feathers, which is a giveaway, and it has latched onto the face, which human beings tend to do, right? And the neck. So if you really think what makes a goose or duck, right, a swan. So it is mixing up its swan, ducks, and goose, but we'll sort of forgive it, right? So it's doing, yeah. Then, and so there are a couple of different techniques you can use, gradient sharp and so forth. So what has happened is that there has been a whole body of work, all leveraging that basic idea that gradients are measures of sensitivity and so forth. And all those 2-3 ideas and the attention map and things that I taught you, a lot of variations of that. And using this, you come to this map, right? And then the other approach was occlusion. Which part of the image, if I remove, will my score become the lowest? Right. So it seems to be paying a lot of attention to the top. Do you notice that? Guys, do you see this? It's for some reason is paying a lot of attention to this, that if you remove these parts, it won't be able to tell what it is. It won't be able to classify as well. So
Probably
that
would think
part
it's a
of it,
pillow.
especially the beak, seems to be the most critical for the model to predict.
So see, what I'm wondering here is, so if this image were the image of the swan, if it were shrunk, let's say 50%, is it likely that it'll show the same area in terms of what it uses to distinguish, or do you think it'll change?
If there are enough pixels, you can assume that it will. The reason for that is, remember in convolutional net, we learned about the affine transforms. The features that you discover are invariant of location and size.
Okay. So
it is its strength and its weakness.
Okay.
So guys, is it fun? I don't know.
Ask one question.
Yes.
So the picture is the input to the model itself, not to the LIME or the datum or CAPTAM package, right?
Yeah.
And CAPTAM is just actually trying to explain how the model came to the conclusion that it's a goose.
Exactly. See, the way it works, Rafiq, is just to recap. You take this picture, you give it to the model, it will come up with a prediction. It will say, I don't know, what did it say? It said goose, right? Now you go to CAPTAM and say, explain to me why did this model say goose, right? So then using one of the means within CAPTAM, all this attention, grad, so on and so forth, it will say, oh, it called goose because it was paying attention to these features in the image.
Right, yes, got it.
So I think ours is, the picture is given.
Look at this and then you ask a question. Sorry, picture is given as the input to the model and to the CAPTAM also, because you're asking it to see. The way you do it is, okay, here is a model. If you give the picture to the model, it will make a prediction. Now you give to Captain, you say, okay, here's my picture, here is my model. Explain what in this picture this model is seeing. Do you see that? So then,
and you're also saying this is the label. Goose is given as input to the Captain as well, like the label output prediction.
Typically, you don't, because you're just looking at the derivatives. If you think about it, visualization, transpose, original, you notice that you traditionally don't give. I mean, you don't need to, because it's looking at the derivative of the gradients, the derivative with respect to the input. Remember if you remember this formula.
Okay.
You
so
see,
I thought it was the other way.
Yeah. So some algorithms do it. So it depends on that, which algorithm. But this particular gradient based, remember, what are we looking at? We are looking at the gradient with respect to the input. You see this expression here, right? And that I generalized to this, the gradient of y with respect to the input. Gradient of the response with respect to the input. So what it does is it can compute it. Some libraries will say, give me both. Yeah. Or some libraries will say, if I have the input, I can produce the output on my own from the model. Remember, it has the model, right? But the two things that you must give is the input and the model. Otherwise, it won't know what to explain. And if you don't give the input and if you don't give the model, it will not know what model it is trying to explain.
Because the reason I'm asking is it's a multi-class problem here. So there could be a duck, goose, swan, and we need to know in the picture what the model needs to explain. Does it?
So let me answer. See, here's the thing. This particular problem with NestNet, the way it has been trained is on a large class of objects. So getting swan and goose mixed up, like pretty much is doing very well. It's a bird. It's a water bird, right? Because they are trucks, they are aeroplanes, they are God knows pencil and whatnot. Right?
Where did this notebook come from?
This is literally from the Captain website.
Okay, thank you.
So I'll walk you through all the lovely tutorials they have in a moment. But I want you guys to understand that this, in a way, tells you what the neural network is seeing, where it is paying attention to. Right? And so the homework that I'll give you guys is do this. In this code, right, all you have to do is go to this directory. Where is this? You see this directory and change this with some other object in the ResNet. When you run this, you'll get your ResNet data. Change it with something else. Make it a dog, make it a house, make it a truck, aeroplane, whatever it is that you want it to be, right? And then run it again and see what is the neural network paying attention to. You will see something interesting. You'll see how the neural network thinks. Are we together, guys? Right. So, guys, is it understandable? I think that this is quite straightforward, isn't it? Any confusion so far?
No, not now that I know where the notebook's from.
Yeah, that's right. It's straightforward. Yeah.
Asif, there are too many techniques. There are like at least 10, 20 different techniques brought under Captain, which also includes Shapely within it. And I went through all of them. It's too difficult for me to, few of them you described, I understood, but the rest is difficult.
Would you like to understand all the rest? So let me do one thing.
Yeah, certainly. I need to actually.
Okay, I'll keep in, one of these Sunday sessions or something. I'll keep See, behind all those techniques, the papers that are there, I'm familiar with those papers. So I can explain those to you. They're not very different. Like once you get the big idea, the gradient and the activation map to core ideas and the back propagation is being, stopped, right? And so on and so forth, the filtering and so forth. There are only 3, 4, 5 good ideas. Now you start mixing them up. And then you throw Shapely into the mix also while you're at it.
Yeah. They are mixing Shapely and the integrated gradient, forward pass, backward pass, recon.
Yeah.
There's a lot of them they are mixing.
You can do a lot of fun stuff with that. But, you're just doing permutation and combination of just a few small set of ideas.
Mm-hmm.
So, but there are a lot of papers that have come, and if you really look at it, right, I mean, I'm sure that the researchers did excellent work, but in hindsight, they all looked like, okay, a small set of good ideas mashed together in hindsight. So let's go to the Captain website, guys. And there are a lot of, so I strongly encourage you to go to the Captain website, and you will see a lot of explanations. It explains BERT, it explains the word, which words and so forth. So let's start with Captain. It gives you this one, Hunger. Let me just make it big. Yeah. It gives you obviously a lot of examples with things. It will tell you this is your average feature importance in a global perspective, right? This and that and so forth. Okay. I won't go through this. By now you understand what feature importance is, positive and negative. So the first example is too trivial. Let me interpreting vision with CFAR. So yeah, this is CFAR. Let's see what it is looking at. What it is doing is integrated gradient, saliency, dip, lift, all of these are common things. I didn't teach you the noise tunnel, but it basically has to do, let me remember, noise tunnel has to do with the backprop. Okay, I'll remember, I've forgotten. Okay, so you take the CFAR data. CFAR 10 means there are 10 classes, right? What are those 10 classes? Plane, car, bird, cat, deer, frog, etc. Let's see how well it does. Now, do you remember that CFAR 10 has been trained in very, very small images? I believe they're just 32 pixel by 32 pixel, tiny images by modern world standards. This class, guys, when you look at it, tell me that this looks like basic neural net. Couple of 2 conv layers followed by dense layer, and then you're done.
Yes.
Easy code, right? Now, by now you should be. Why cross entropy loss? Because it's a classification problem, one of the 10 classes. This is the standard, training loop. You run that. What have you done after you have trained it? Okay, you're predicting. Ground truth is cat, ship, plane, and it is predicting cat, ship, ship. It's calling this a ship, not a plane, right? Actually, there's so little pixel of information, I can quite understand why you would consider it a ship. But okay, let's see. Now ask it to explain. This was a ship. Yeah. Original image, so the one that it got wrong. This was the one that it got wrong, right? Let us put the gradients and see where is it paying attention to. So it turns out it is paying attention here, a little bit more here. It has latched onto the fact that this is most important, right? And if you look at this part, it actually doesn't quite see the, can you just look at this and say that it is a plane? If you're paying attention here?
That's really hard to tell.
It's very hard to tell. So this is the one it got wrong. This is another example. Oh, it is the same example. Here's a feature ablation example. What is feature ablation? Covering it up, right? So you look at this image. This is, by the way, often quoted image. There are 3 wine bottles and a computer and a lot of clutter in the background, right? So if you do image segmentation, you'll say 3 bottles and a couple of screens, right? So suppose you have to tell the wine bottles, right? Classify the image, and you classify the image as wine bottle. If you think about it, let's look at the influence map for this. So things that are deep green convinces you more and more. They have strong impact in helping you classify it as wine bottles. Would you agree that this region, this deep green things, this region, these pixels will help you decide that it is or strongly convince you that it's a wine bottle?
That's a very good match.
Yeah, it's almost, yeah, perfect match. At the same time, these have negative impact. Means it says that this is clutter. This is actually unconvincing you that these are wine bottles, right? It reduces your conviction that these are wine bottles, isn't it? This screens, because the screens are the clutter. What happens if you remove, so this is again, you do that. I think you can check that if there's an occlusion, right? So inspect the influence part of alternative classification. If you were classifying it as screen, computer screen, I believe that's what they're doing here. Let us compute is the same image, class ID 664. Okay, as a class as a TV monitor screen. So if you want it to be TV monitor, then what? These two become the positive factors for Shapley, right? Or for the, sorry, for the positive influence. Yeah. And what do these things become? The wine bottle become the distraction. Yes, exactly. They unconvince you, or so they shake up your conviction that these are screens. Yeah. And so what you do is, suppose you apply a mask, a black mask here, and then reclassify the image. What is it predicting? It is predicting it's a desktop computer, right? Output is a desktop computer. The pointer class is amongst the top 5. So this is it. Yeah. So this is a way to understand how the computer, how the neural network is understanding things. And you can do it with, I mean, obviously the simpler ones are the Boston housing price, right? You guys all know we have done, do you guys remember doing Boston? We did Boston crime. We didn't do the Boston house price, did we? In ML100, we did Boston.
Yeah, and R. And...
Yes, we did. We did some of these. So yeah, it's a very straightforward data set. You can look it up. Now, I won't go into too much detail, but if you look at the different attribution algorithms, they will have slight differences though, but they will all more or less agree. So this is one, then nothing very different. You just have to become familiar with the API. And all these APIs are straightforward. And with that, guys, this is your lab. So what are we supposed to do? I'll also post this XAI notebook in the website, and I'll also post these links. Yeah, these links are already there on your course portal, but I'll also post it to Slack. Now, I would strongly suggest that, for example, go to Shapley, these examples, try to reproduce it, guys. Bring it into your own notebook or download this notebook and reproduce it. It is really worth reproducing it. And you see here it is, playing with this in your own notebooks. Right? Take all of these examples and play with it, and then apply it to your data set. In fact, apply it to the California housing data set. This is that. Then again, you can apply it, Chef, for PyTorch also. When you do that, this is this. So play with this MNest and play with all of this. Play with Lime. The Lime website again has, this is Chef. The Lime again has a lot of examples, right? So here it is. So look at this image. What factors convince you that it is a cat? The green ones, and what is sort of reducing your conviction that it's a cat? The dog here. Does that make sense, guys?
Yes.
Right. So this is it, after a little while, it all begins to look very intuitive. These tools are very powerful tools. I believe you should ensure, you should use it every single time that you do model building. You train a model, must go and do create explainable models, guys. Create explanations for the model after that. It is doing due diligence. Otherwise, it can lead to a lot of grief. So I'll stop with that. And any questions? Guys, do these labs, and the ones that you see here, Captain, Lime, and Shapley, these 3. Just go and learn about these 3 and learn to use them. API, as you notice, was very simple. I showed you in my notebook. Very, very simple. A couple of lines, 3-4 lines for each of them. Maybe 5 lines.
My California housing shop is at 16% now.
Making progress. Good.
One question, is there any, we have these 3 different libraries. Is there any specific field that we can use or or specific types of models to explain, or they all can be equally applied to any type of model?
For deep neural networks, then, you have to look at gradient-based methods because they will be faster than SHAP. SHAP can be computationally brutal, like Kate is finding out by running the notebooks. Right? The gradient-based methods will converge very quickly. There's gradient maps and things. So anything that has grad in it, a grad cam, so gradient and attention map put together, just the gradient thing, it's a gradient map itself. Then gradient SHAP, grad SHAP, yeah, which hybridizes Shapely with grad. So usually if you're dealing with neural networks, bring in your grad-based something, yeah, or attention-based something. Then so not attention, activation. Why am I saying attention? Activation-based activation map. But these ideas are cool. But if you're outside the deep neural network thing, then you can't quite get into that. Actually, you can use those ideas, but generally, Shapely and Line are your tools, or they are my go-to tools. Right? The SHAP in particular, I use a lot, simply because of so much you can, unpack and understand from its graphs.
So, Asif, the CAPTM also includes Lime and Shapely libraries now inside of it.
Oh, inside of it, is it? Okay,
yeah.
interesting.
They have a gradient SHAP and kernel SHAP.
It's different. Gradient, I see. Putting the things together, it's not different.
I see. But the Lime is also supported here. If I just overviewed a couple of times.
Yeah, nice. Oh, good. I'll explore this more and see what else it has. There's a wealth of information, guys. These are not the only libraries, but these are certainly good libraries. If you stick with these, pick it up. You can pick it up in 3-4 days and use them for the rest of your life. All right, guys. So with that, I am done with explainable AI at this moment. There are many techniques we haven't covered, but if we have to cover it all in a week, I suppose we learned enough. I introduce you to a field and now you can go and explore more and more and more. Balaji, you feel, because you really cared about this topic, did you feel you learned something in this week?
Yes, actually, even before you started, I went and saw that particular package you had listed. That's where I started getting the idea of which paper. Shapely is where I started.
Okay.
And those were the ones which helped me.
Yeah. So, yeah. Good, good. Anybody else who's going to use this stuff, explainable AI? Use it, guys. Use it. Anybody who's totally confused and needs a review? So we all seem to have understood, isn't it? All right, guys. So this is great.
So Asif, on an ending remark, I want to say something.
Yes.
In my team, there are like people doing image modeling, text modeling, combined modeling, everything. And by just having an expertise in this particular tool, I can work with all of them and learn all of them.
Yes, yes.
While also contributing to their work.
Yes.
Which is very interesting.
Yeah. See, at this moment, it's a very low-hanging fruit, Balaji. Most people don't think about this. They will train the model, very due diligence, religiously. They will look at the performance on test data and report it. But that is not enough. This is the very low-hanging fruit. You bring value into an organization just by doing this.
And we see a lot of team, there's a backlash from a lot of team because they couldn't understand the models our team builds and it doesn't perform well in certain areas. And they go to rule-based. They don't have belief in neural networks.
Yes, all they need to do is just do that, the gradient maps. You just make the map and see why is it classifying this. For example, that aeroplane, right? Or why was it being classified as a ship? And soon you understand why, right? You understand where it is getting confused. And once you know that, you can then tweak your algorithms. The neural network, it's very easy to tweak it. Hand tweak it.
I think the pre-processing tokenization is where the NLP will benefit a lot from understanding that.
You know, when it predicts that this is a positive emotion, it will tell you, it will highlight the words, hotspot the words that it paid attention to. You know, bird-based. That is the bird-based stuff. Okay. So, by the way, we are looking at it here. Remember, this is much better done. I introduced you guys to Allen NLP. Okay, anyway, so you see this highlighting of words. But for this, I would like to just remind you, Allen NLP, that I introduced you to. Let's see. Oh, goodness. Let's choose a text. How many run? Right? And it picked up 2, right? If you ask for a simple gradient visualization, what is this, guys? Integrated gradient visualization, smooth grad. Right? This is one reason I have been saying to you guys that saliency map. Now, do you understand this, guys? These words you would not have understood before this week from Allen NLP. Yeah. And remember, for NLP, I said just stick to 3 main libraries. One is Allen NLP, Hugging Faces, and Spacey. Right? And see, it is telling you, right? It is telling you where it is paying attention to, the gradient map. Here is the integrated gradient map. You can ask it to interpret. Actually, this part I love about Allen NLP, that it has, being a very modern library, it pays attention to interpretability or explainability. And so you see it here come through. There, see, I missed a couple of topics. For example, the adversarial attack. There is this classic thing that people realize to their great surprise. You take a perfectly good red car, you give it to the neural network and it says car. And then what you do is you take noise and you add noise to the car. And then what you do is you keep shaking the noise, you keep changing the noise shape so that its confidence in car keeps going down. And suddenly it is not recognizing this as a car, but it's calling it something else, maybe a boat, or I don't know, whatever else it is. It is calling it something completely different. And so what you have done is you have done an adversarial attack with a noise, which if you impose on the image, to the human being, it still looks like a car, but the neural network is now confused. Right. So there are all sorts of things, interesting side plots and themes here in this world of explainability. So I won't go more into it. Please do go play. One nice thing with Allen NLP, this demo, is that you can see a lot of this interpretability in action. So please take this as a homework and play with this too. So this one, Balaji, for you will be useful for your textual part.
Yes, I think one of the authors 3 years ago who published this Shapely package is from the Allen NLP team, I guess.
Oh, he's joined there. No wonder he's brought all his assets here.
Yeah, so that's where I started looking at the Shapely paper. I think his name is Lundberg, or I don't know exactly the.
Yeah, that's right.
University of Washington. Yes.
This is the person, Lundberg.
Yes.
Yeah, that's one. So he has now joined Scott Lundberg. He has joined Allen NLP has a lot of momentum. That's why I say Spacey, Allen NLP, and the Hugging Faces. Most of your NLP tasks are taken care of. For semantic modeling, Jensen, that's it. I personally almost rarely ever use NLTK and other libraries.
So our third homework assignment is to do what with Allen NLP?
Just go and play with it on the website. You know, when we went to, where's the Allen NLP? Yeah. See, play with it and see the interpretability, how it is interpreting it. Right. See, for example, all of these visualizations. At this moment, it has hung because it's obviously computationally a bit brutal for it. I don't know what it will do now. Okay. All right, guys, that's all there is to it. That finishes our last lab. I am very eager to guide you guys on the project. So coming week, we should start. One of the things I'll do is, you guys don't know how to take a machine learning model and take it to production in a high performance way. Like create, for example, a native Linux binary out of it. Right? And
that I'm interested in.
yes, and then take it to, I don't know, take it to Kubernetes, scale it out, deploy it. Those are important things, guys. If you can do end to end, you can be a one-man startup. You have picked up a lot of things. You guys have all gotten interested in Streamlit. I hope some of you did React. Some of you took some other approach, I hope. Right? Your different approaches to the UI. Some of you did it in plain HTML. That's all good. You all picked up a little bit of REST or microservices, but you haven't picked up some of the ways to make it robust and scalable so that you'll survive when large traffic comes and hits your portal, your application. Most, the irony is that a lot of companies die on the first day because they can't take the traffic. And then people get a bad impression and they never come back. Apparently, it's a known thing in the user interface world and site reliability and all that. All right, guys, that is it.